situated in the heart of the Research Triangle Park in central North Carolina. Carolina Physics and Astronomy is a prominent hub for the perpetual pursuit of understanding the mysteries of our universe and understanding of the questions and challenges of our everyday lives. University of North Carolina at Chapel Hill is the oldest public university in the nation. And our department has been the home of many physics luminaries, from Nathan Rosen to John Wheeler and Bryce DeWitt and Cecil DeWitt, to Peter Higgs, who is known for the Higgs particle. We actually study how nature works, how the world actually works, starting from the very small, the basic building block of our universe, the smallest particles in this universe, to the cosmos, to the largest, expand the entire universe.
In my lab, we study a particle called the neutrino. This is a very light, neutral particle, and it barely interacts. So what that means is that you have billions of neutrinos going through your body all the time, but they may interact just a few times over the course of your whole life. We're interested in this particle because it could tell us why there's more matter than antimatter in the universe around us. We look around us and we see a universe that's full of matter. We see about 10 billion times more matter than antimatter. But nothing in standard model physics can break this balance that we've found. And neutrinos are the one fundamental particle that could be its own antiparticle. And that means that they could undergo a decay that breaks the balance of matter and antimatter. They could be their own antiparticle and explain why we see a universe full of matter. This research is important because it tells us about the universe around us, right? We can't build a collider that recreates the conditions right after the Big Bang. It's just too high energy. So what we do instead is we go to the low energy and search for signatures of these very high energy processes. And that means looking for very rare processes. Understanding neutrinos is really key to understanding fundamental physics because they're the one solid piece of evidence that we have that what we call the standard model doesn't explain everything. And so there's sort of like a loose thread that we can tug on to unravel some of these mysteries.
Being a student here is awesome. I really like the program. There's a lot of support from the faculty and the advisors and the professors to really engage with the material and dive deep into what interests me.
If I was talking to a student who wanted to come to UNC, I would tell them this is a very welcoming and fun place to be. I have enjoyed my time, and I think it's provided many great opportunities for myself, and I think it can provide them with those opportunities too.
Today, we're primarily developing medical imaging devices utilizing the carbon nanotube X-ray source array that's actually originally invented by our lab here at UNC. For example, in the last couple of years, very recently, we using the nanotube X-ray technology, we developed a quasi-3D dental imaging device with the initial engineering development at the physics department. Then we carry out a clinical study at our dental school. That technology has led to a startup company who has further developed the technology and obtained FDA clearance. Now the product is on the market for patient care. I think in the future you'll see more imaging technologies that utilizing this unique carbon nanotube X-ray source array that we originally developed here at UNC Chapel Hill.
Being a student here, especially a graduate student here, definitely can be challenging at times, but I really enjoy the people that I get to work with. It's provided me a lot of opportunities to travel that I wouldn't have otherwise.
I love getting to work in this department. I'm getting to work on technology like carbon nanotube X-ray emitters, which are being used in the hospital and implemented right now.
So the Argus array is a new type of telescope that combines 900 mass-produced telescopes to cover the entire sky in every exposure. So it looks for events as fast as 1 second across the entire sky and is designed to build up a movie over many years of all the cosmic events happening, which will allow us to explore a whole new parameter space in astronomy. One of the things I'm most excited about for the Argus Array is its potential to contribute to multi-messenger astronomy. When events are seen by gravitational wave detectors, by neutrino detectors, by X-ray or gamma-ray satellites, those events will also be recorded by the Argus Array, at least for a large section of the sky, and we'll have a movie of what was going on in those regions optically, even if the event is not obvious in the initial optical data from the Argus Array or all other telescopes. And this means for the first time we'll be able to see, for example, prompt flashes associated with gravitational wave events, where traditional telescopes would be completely unable to reach those events in time.
Most excited about this work is that we can answer some of the most important questions to humankind. Where do we come from? Where are we going? Are we alone in this universe? Now, it may not seem like it directly impacts those, but the kind of work I mentioned really addresses those questions. Yeah, where do the matter actually come from? How do they interact? How does the cosmos come to be? And whether there are any living life out there.